Superposition. Superposition is a super useful technique to add to your toolkit of circuit analysis methods. Use superposition when you have a circuit with multiple inputs or multiple power sources. The principle of superposition is another name for the additivity property of linearity, where the function of x sub 1 plus x sub 2 is equal to the function of x sub 1 plus the function of x sub 2. To solve a circuit using superposition, the first step is to turn off or suppress all but one input. To suppress a voltage source, replace it with short circuit. To suppress a current source, replace it with an open circuit. Then, you analyze the resulting simpler circuits. Repeat for all inputs. The final result is the sum of individual results. Now, let's describe a circuit as a function. The principle of superposition is defined using functional notation. So we talk a bit here about how circuits can be represented as functions. Starting simple. How could we represent a lone resistor using the notation of a mathematical function? There's nothing remarkable going on here. I'm just talking about Ohm's law using function terminology. We begin by identifying the three things: the inputs, the thing performing the function, and the outputs. I decided that voltage V sub I will be the input to our resistor function. We can assume that the input V sub I is generated by some voltage-making thing we're not showing. We assign the output to be the interesting thing that we want to know. For this function, the output is the current I in the resistor. The input voltage is applied to the two small circles. The function itself comes from the resistor by means of Ohm's law. The output of our function will be the current I measured by some not shown current meter. Written as a function, our resistor is I equals to the function of V sub I is also equal to 1 over R multiplied to V sub I. With this notation, we are viewing that the resistor as a function takes in a voltage and outputs as a current. Looking at our resistor function, we see it has a scaling property. The output I equals to input V scaled by a constant R. That means that the resistor is linear. The linearity property is what triggers our ability to use superposition to help solve this circuit. Let's say that the input to our function is two voltages in series. The input to our function is two batteries in series where V sub I is equal to V sub S1 plus V sub S2. The function of V is equal to 1 over R multiplied to V. As you can see, the output of the function hasn't changed. Now here is your linear function. It says that if you have two inputs superimposed, x sub 1 plus x sub 2, you can apply the inputs one at a time, x sub 1 followed by x sub 2, and then add the individual results to get the full answer. Now let's use the principle of superposition to solve the circuit. Since we've modeled our circuit as a function, we can say that I is equal to the function of V sub S1 plus V sub S2. It's also the same with I is equal to the function of V sub S1 plus the function of V sub S2. This suggests an intriguing possibility. It says that we can compute the output current the conventional way by applying the combined inputs to the function of V sub S1 plus V sub S2, or we can get the same answer by computing the function with single inputs, function of V sub S1 and function of V sub S2, and adding the results together. To apply superposition, we need to apply the inputs one at a time. That means we have to turn off all inputs except for one. When we turn off an input, we say it is suppressed. What does it mean to turn off a voltage source? It means we set the value of V equals to 0. This is the same thing as replacing the voltage source or the battery by a short circuit. While turning off the current source means that we have to set the current equals to 0. That's the same as replacing current source with an open circuit. In the next two schematics, one of the voltage input has been turned off by replacing it with a short circuit. When we zero out or suppress an input, we replace one of inputs with zero, allowing the one remaining input to shine through by itself. Now we solve each circuit individually, where I sub 1 is equals to V sub S1 over R and I sub 2 is equals to V sub S2 over R. I sub 1 is the current caused by the source V sub S1 and I sub 2 is the current caused by the source V sub S2. The total current comes from superimposing the currents from each circuit.
I is equal to I sub 1 plus I sub 2, where I is also equal to V sub S1 over R plus V sub S2 over R. It can also be written as V sub S1 plus V sub S2 all over R. Now, what we did here is called the linear superposition of two circuits. Let's have an example. Consider the following linear circuit with two sources, one voltage and one current source. The two sources are the inputs to the function. For this problem, we happen to want to find two outputs, current I sub 1 and current I sub 2. Let's analyze this circuit using superposition. First, we suppress the current source and analyze the circuit with just the voltage source acting alone. To suppress the current source, we replace it with an open circuit. With just the voltage source, the two output currents are I sub 1V is equal to 0 and I sub 2V is equal to V sub S R2, where I sub 1V and I sub 2V are the currents in R1 and R2 caused by the voltage source. Next, we restore the current source and suppress the voltage source. To calculate the contribution of the current source acting alone, with just the current source, the two output currents are I sub 1I would be equal to IS and I sub 2I is equal to 0, where I sub 1I and I sub 2I are the currents in R1 and R2 caused by the current source. We complete the analysis by adding the contribution from each source. Now for I sub 1, we have I sub 1V plus I sub 1I. Now for your I sub 1V is equal to 0 and your I sub 1I is equal to IS. So it will give you 0 plus IS. So your I sub 1 will be equal to IS. Next is your I sub 2 that is equal to I sub 2V plus I sub 2I, where your I sub 2V is equal to V sub S over R2 and your I sub 2I is equal to 0. So this will give us I sub 2 is equal to V sub S all over R2. And now the full solution looks like this. This could have been a tricky analysis because the two sources make it more difficult to write node or loop equations. We exploited superposition, which gave us the two simpler circuits to deal with. And now let's have example number 2. Let's determine the voltage drop and the current across the resistor 3.3 kiloohms as shown in this figure. First, we must remove the 8 volts power supply from the original circuit such that the new circuit will look like this, and then measure the voltage across a resistor. As you can see here, you have your 3.3 kiloohms and 2 kiloohms that are in parallel. So therefore, the resultant resistance will be equal to 1.245 kiloohms. Using your voltage divider rule, voltage across 1.245 kiloohms would be V1 equals to 1.245 all over 1.245 plus 4.7. And this whole equation right here is multiplied to your voltage 5. And your answer would be equal to 1.047 volts. Now let's remove the 5 volts power supply from the original circuit. And now your circuit will look like this. Then measure the voltage across a resistor. Here you have your 3.3 kiloohms and your 4.7 kiloohms that are in parallel. Therefore, the resultant resistance will be equal to 1.938 kiloohms. Again, using your voltage divider rule, voltage across 1.938 kiloohms would be your V2, where your V2 would be equal to 1.938 over 1.938 plus 2, and this equation will be multiplied through 8 volts, which will give us an answer of 3.9377 volts. Therefore, your voltage drop across a 3.3 kiloohm resistor is V1 plus V2, where our V1 is 1.047 and our V2 is 3.9377. So if we add them together, it will give us an answer of 4.9847 volts.